Picture this. You're standing on the edge of an ancient world where nightmare creatures prowl through steaming swamps, where the very air you breathe could poison you, and where death lurks in every shadow. This isn't some fantasy realm from your darkest dreams. This is Earth, hundreds of millions of years before the first dinosaur ever drew breath. Most people think they know prehistoric Earth. They imagine mighty T-Rex stomping through jungles or massive sauropods munching on ferns. But here's the terrifying truth that will completely shatter everything you thought you knew about our planet's past. The world before dinosaurs was infinitely more alien, more dangerous, and more absolutely nightmarish than anything that came after. What if I told you that creatures existed that would make a great white shark look like a goldfish? What if I revealed that our planet once hosted predators so bizarre and terrifying that they seem ripped straight from the pages of a horror novel? What if I showed you evidence of mass extinction so catastrophic that they make the asteroid that killed the dinosaurs look like a minor inconvenience? Today, we're embarking on a journey that will take you back over 400 million years to witness the most terrifying chapter in Earth's history. We'll uncover prehistoric secrets that paleontologists have only recently begun to understand, revealing creatures and catastrophes that will leave you questioning everything you thought you knew about life on our planet. But before we dive into this incredible adventure through deep time, make sure to hit that subscribe button and ring the notification bell, because what you're about to discover will completely change how you see the world around you. Trust me, you won't want to miss what's coming next. Long before the first dinosaur footprint was ever pressed into ancient mud, our planet was a frozen wasteland that would make Antarctica look like a tropical paradise. Imagine Earth as a massive snowball, completely encased in ice from the North Pole all the way to the equator. This wasn't just a harsh winter that lasted a few months. This was a global deep freeze that persisted for millions upon millions of years. The very idea of this frozen Earth seems impossible when you consider that life somehow not only survived, but eventually thrived in these conditions. But here's where the story gets absolutely fascinating and terrifying at the same time. Beneath the ice, volcanic forces were building up pressure like a massive pressure cooker ready to explode. When these volcanic eruptions finally broke through the ice, they released enormous quantities of carbon dioxide into the atmosphere. This created a greenhouse effect so powerful that it transformed our frozen planet into a sweltering hothouse almost overnight in geological terms. The ice melted, sea levels rose dramatically, and the stage was set for life to take its first tentative steps toward complexity. But this wasn't the gentle emergence of life that you might imagine. This was a violent, chaotic birth that would set the tone for everything that followed. The continental masses that had been locked in place by ice began to drift and collide, forming a supercontinent called Rodinia. This massive landmass was surrounded by a single vast ocean called Panthalassa. And it was in these ancient waters that the first truly terrifying creatures began to emerge. As the ice melted and the oceans warmed, something extraordinary and terrifying began to happen. Life, which had existed only as simple bacteria and microbes for billions of years, suddenly exploded into forms that were unlike anything that had ever existed before or since. The first of these creatures was discovered in 1946 by an Australian geologist named Reg Sprigg. He was having lunch in the hills of South Australia when he noticed strange jellyfish-shaped imprints in rocks that were over 600 million years old. What he had stumbled upon would turn out to be one of the most important fossil discoveries in history. This creature, which scientists named Dickinsonia, was like nothing that exists today. Picture an oval-shaped organism that could grow up to nearly 5 feet in length, but was as thin as a sheet of cigarette paper. It was covered in grooves that divided its body into segments, giving it an alien appearance that would look right at home in a science fiction horror film. But here's what makes Dickinsonia truly terrifying from our modern perspective. Scientists still aren't entirely sure what it was. Was it an animal? A plant? Some kind of fungus? Or was it something else entirely, a form of life so alien that we don't even have a category for it? Recent studies have detected fat molecules in fossilized specimens that suggest it might have been an early animal, but even that leaves more questions than answers. What we do know is that Dickinsonia was just the beginning. As conditions on Earth continued to change, more and more bizarre creatures began to appear in the fossil record. There was Charnia, a fern-like organism that lived in the deep ocean where no plants could possibly survive. Some specimens of this creature grew to over 6 feet in length, swaying in the ancient currents like some kind of underwater nightmare. Then there was Kimberella, a creature that might have been the ancestor of modern snails. It had a wide, muscular foot for moving around and a shell that it could retract into when threatened. But what makes Kimberella particularly unsettling is that it left behind feeding traces that show it was actively hunting and consuming other organisms. This was one of the first predators in Earth's history, and it was already perfecting the art of the hunt over 550 million years ago. As these early creatures continued to evolve, something truly significant happened that would forever change the nature of life on Earth. The first animal to develop a shell appeared in the fossil record. This creature, called Cloudina, might not seem particularly threatening at first glance. It was only about 6 inches long and lived in a tube-like shell made of stacked cones. But the appearance of shells marked the beginning of an evolutionary arms race that would escalate into some of the most terrifying conflicts in natural history. You see, shells didn't evolve for protection against the elements. They evolved for protection against other creatures that were trying to eat them. Scientists have found Cloudina shells with holes drilled through them, clear evidence that other animals were actively trying to break through their defenses. This means that by 550 million years ago, the peaceful world of early life was already becoming a battlefield where creatures were locked in a constant struggle between predator and prey. This arms race would continue to escalate throughout the following millions of years, producing creatures that were increasingly bizarre, increasingly dangerous, and increasingly terrifying. The stage was being set for what paleontologists call the Cambrian explosion, an event that would unleash some of the most alien and nightmarish creatures that have ever existed on our planet. As life was becoming more complex and more dangerous, the Earth itself was undergoing dramatic changes that would reshape the entire planet. The supercontinent Rodinia, which had dominated the globe for millions of years, began to break apart in a process that was both gradual and catastrophic. Around 560 million years ago, three major land masses separated from Rodinia and began drifting apart. Laurentia, which would eventually become North America, split off first. Siberia, corresponding to what we now call Russia, became its own continent, and Gondwana, a massive landmass that included what would become Africa, South America, Antarctica, India, China, Southeast Asia, and Australia, began its own separate journey. This continental breakup wasn't just a geological curiosity. It had profound implications for the evolution of life because it created new ocean basins, changed global weather patterns, and isolated populations of creatures that had previously been connected. As these continents drifted apart, they carried their unique assemblages of life with them, setting the stage for different evolutionary experiments to unfold in different parts of the world. The opening of new oceans also created new opportunities for life to diversify and spread. Ocean currents began to flow in different patterns, bringing nutrients to new areas and creating new ecological niches that could be exploited by emerging life forms. But these changes also made the planet more unstable and unpredictable, setting the stage for the catastrophic events that would follow. About 540 million years ago, something happened that paleontologists still struggle to fully understand. In what seems like an instant in geological time, life exploded into an incredible diversity of forms that were unlike anything that had come before. This event, known as the Cambrian explosion, marked the beginning of the Paleozoic era and the emergence of complex animal life. The most famous fossil site from this period is the Burgess Shale in British Columbia, Canada. Discovered in 1909, this site has yielded some of the most bizarre and alien-looking creatures ever found in the fossil record. These aren't just strange by the standards of their time. These are creatures that would look completely alien even by today's standards. One of the most unsettling of these creatures was Hallucigenia, a name that perfectly captures just how bizarre this animal was. Picture a creature about 2 centimeters long with a soft trunk covered in spines. It walked on 10 pairs of legs that looked like stilts, giving it an otherworldly appearance that would be right at home in a nightmare. But here's what makes Hallucigenia truly terrifying. It had a mouth surrounded by teeth, and its throat contained a second set of needle-like teeth. This means that any prey unfortunate enough to be caught by this creature would be chewed not once, but twice. The first set of teeth would tear the prey apart, and the second set would finish the job as the food was swallowed. Scientists have also discovered that Hallucigenia had a pair of dark spots on its head that were probably eyes, meaning that this nightmare creature could see its prey coming and plan its attacks accordingly. Recent advances in microscopy have revealed that this creature was related to modern velvet worms, animals that still exist today in tropical forests and are considered to be relatives of arthropods. As the Cambrian period continued, creatures began to develop increasingly sophisticated defensive mechanisms. One of the most striking examples of this evolutionary arms race was Waiwaxia, a creature that looked like it had been designed by a medieval armorer with a twisted sense of humor. Waiwaxia had an oval-shaped body about 2 inches long that was covered with 8 rows of overlapping plates called sclerites. These plates acted like armor, protecting the creature from predator attacks. But that wasn't enough protection for this paranoid little animal. On top of the armor plates, Wiwaxia had 2 rows of spikes that could reach up to 2 inches in height. But here's where things get really interesting and disturbing. The scales of this natural armor were loaded with microscopic structures that reflected light, like the back of a beetle. This created a dazzling effect that would have been enough to confuse and deter potential attackers. It was like having built-in disco ball armor designed to blind predators. Even more bizarrely, examination of Wiwaxia fossils has revealed that other creatures actually lived on its back. Shells similar to clams have been found attached to Wiwaxia specimens, suggesting that this armored creature served as a mobile home for other organisms. It's as if this creature was so well defended that other animals felt safe enough to hitchhike on its back. Scientists still debate what Wiwaxia actually was. Some think it was related to modern marine worms. Others believe it was an ancestor of snails. Still others think it represents a completely extinct group of animals that has no modern relatives. The fact that we can't even figure out what category this creature belongs to just adds to its alien and unsettling nature. But if you want to talk about the true rulers of the Cambrian seas, you have to talk about trilobites. These creatures were absolutely everywhere during this period, occupying every conceivable ecological niche from coral reefs to the deepest ocean floors. For over 270 million years, trilobites dominated marine ecosystems in a way that no single group of animals has ever done before or since. To date, paleontologists have identified over 20,000 different species of trilobites, and new species are still being discovered regularly. They came in an incredible variety of shapes and sizes, from tiny creatures no bigger than a fingernail to monsters that reached over 2 feet in length. Most species were between 1 and 4 inches long, but their diversity was absolutely staggering. What made trilobites so successful was their incredibly sophisticated body plan. Their bodies were divided into 3 parts, both lengthwise and widthwise, which is where they got their name. They had a head composed of 3 lobes, a thorax, and a tail. The head included compound eyes made up of hundreds of facets, similar to those of modern dragonflies. But here's what makes trilobites truly remarkable and somewhat terrifying. They were probably the first creatures on Earth to develop sophisticated vision. Their compound eyes were incredibly advanced, allowing them to see in multiple directions simultaneously and detect movement with remarkable precision. This made them formidable predators and gave them a significant advantage over other creatures in their environment. The diversity of trilobite body forms reflects the incredible variety of lifestyles they adopted. Some were predators that actively hunted other creatures. Others were scavengers that fed on dead organisms. Some filtered nutrients from the water, while others burrowed through sediment looking for food. Some species even developed bizarre spines and projections that made them look like underwater aliens. What we've uncovered today is just the tip of the iceberg when it comes to the terrifying world that existed before the dinosaurs. We've seen creatures that would make your worst nightmares seem tame. And we've witnessed the beginning of evolutionary arms races that would escalate into conflicts more brutal than anything in modern nature. But this is only the beginning of our journey through deep time. In the next part of this series, we'll dive even deeper into the prehistoric world to uncover creatures that make everything we've seen today look like harmless pets. We'll explore the rise of the first massive predators, witness catastrophic mass extinctions that nearly ended all life on Earth, and discover how these ancient nightmares paved the way for the world we know today. If you found today's journey through prehistoric Earth as fascinating and terrifying as I did, make sure to hit that like button and subscribe to the channel with notifications turned on. Trust me, you won't want to miss what's coming next, because the creatures we'll encounter in Part 2 will make everything we've seen today look absolutely tame by comparison. Drop a comment below and let me know which of these prehistoric nightmares surprised you the most. And remember, this incredible story of life on Earth is far from over. The most terrifying chapters are still to come. Among the most puzzling creatures swimming in these ancient seas was something paleontologists nicknamed the lace crab. This bizarre animal, known scientifically as Marella, was discovered in massive quantities in the Burgess Shale, with over 25,000 specimens found in a single location. That's more fossils than most creatures leave behind in their entire evolutionary history. Picture a creature about an inch long with two long extensions sprouting from the top of its head, curving backward like some kind of organic antenna array. Below these extensions, it had multiple pairs of slender appendages near its mouth, probably used for navigation along the sandy bottom of ancient seas. But here's where things get really strange. It had another pair of more robust appendages, covered in hair-like structures that might have been used for propulsion. The rest of Marella's body was composed of up to 26 segments, each potentially serving a different function. Scientists have proposed multiple theories about how this creature fed, but none of them are particularly comforting. It might have been a hunter and scavenger, prowling the seafloor for dead or dying organisms. Or it might have been a filter feeder, using its multiple legs to strain tiny creatures from the water, like some kind of living net. The fact that we still don't know exactly how this incredibly common creature made its living just adds to the alien nature of this ancient world. Imagine if aliens visited Earth today and found millions of human skeletons, but couldn't figure out what we ate or how we obtained our food. That's essentially the situation we're in with Marella. But if you want to see something that truly looks like it was designed by a committee of mad scientists, look no further than Nectocaris. This creature was so bizarre that paleontologists initially thought they were looking at pieces of several different animals that had somehow gotten mixed together in the fossil record. Nectocaris had a cylindrical body that was soft and flattened when viewed from above, measuring between 2 and 5 centimeters in length. It possessed 2 lateral fins that made it look like a hybrid between a ray and a squid, allowing it to swim with surprising agility through the ancient waters. But that's where any resemblance to modern creatures ends. From its rigid head extended two long tentacles that it probably used for hunting or navigation. Even more disturbing, Nectocarus had a pair of rod-shaped eyes that gave it an otherworldly appearance. But perhaps most unsettling of all was the flexible cone that opened from the base of its mouth into an internal cavity containing gills. This cone-like structure was remarkably similar to the siphon that modern cephalopods use to propel themselves through water. Scientists believe that Nectocarus used this organ to shoot jets of water, allowing it to dart through the ocean with sudden bursts of speed. Imagine a creature that could appear calm and motionless one moment, then suddenly rocket through the water like a living missile the next. The hunting strategy of Nectocarus was probably focused on small organisms like plankton and bacteria, but its ability to move with such sudden speed would have made it a formidable predator in its size class. The fact that this creature shares so many features with modern octopuses and squids suggests that it might have been an early ancestor of these intelligent and often terrifying modern predators. Just when you think the creatures of the Cambrian seas couldn't get any more bizarre, along comes Opabinia, a creature so strange that it almost defies description. This 7-centimeter-long animal had a soft, segmented body that gave it a superficial resemblance to a shrimp. But that's where any similarity to familiar creatures ends. Opabinia had 5 eyes. Not 2, not 4, but 5 eyes arranged in a pattern that seems almost deliberately unsettling. 2 eyes were positioned at the front of its head, while 3 more were located at the back, giving it nearly 360-degree vision. This meant that Opabinia could see predators approaching from almost any direction, making it incredibly difficult to surprise or ambush. But the most disturbing feature of Opabinia was its feeding apparatus. Instead of a normal mouth, it had a flexible proboscis that ended in a claw-like structure. This proboscis could extend and retract like some kind of organic fishing line, allowing Opabinia to snatch prey from a distance before pulling it back to its mouth. Without powerful jaws, Opabinia had to limit itself to soft-bodied prey, probably extracting worms and other small creatures from the sediment. Its 15 body segments were bordered by articulated lobes that helped it crawl along the seafloor and swim through the water. The fan-shaped tail fin provided additional propulsion and steering, making it a surprisingly agile hunter, despite its bizarre appearance. Many scientists initially dismissed Opabinia as a unique evolutionary dead end, but more recent research suggests that it might have been related to arthropods, the group that includes modern insects, spiders, and crustaceans. This means that this 5-eyed nightmare might actually be a distant ancestor of some of the most successful animals on Earth today. All of these creatures, strange as they were, pale in comparison to the apex predator of the Cambrian seas. Anomalocaris was a monster by any standard, reaching lengths of up to 3 feet and dominating the ancient oceans like a living nightmare. Its body resembled that of a giant shrimp, but it was armed with features that would have made it absolutely terrifying to encounter. The most distinctive features of Anomalocaris were the spike-covered appendages that hung beneath its head like organic grappling hooks. These powerful arms could seize prey with devastating efficiency, while its round, flattened mouth worked like a camera shutter, opening and closing to crush whatever unfortunate creature had been caught. The preferred prey of Anomalocaris appears to have been trilobites, based on bite marks found on fossilized specimens that perfectly match the predator's jaw structure. However, some paleontologists have suggested that Anomalocaris might not have been able to crack the hardest shells, limiting it to feeding on trilobites during their molting periods when their armor was soft and vulnerable. But even if Anomalocaris couldn't always penetrate the heaviest armor, it was certainly a threat to the countless soft-bodied creatures that inhabited the Cambrian seas. From Greenland to Australia, dozens of Anomalocaris specimens have been found in rocks from this period, suggesting that these predators were widespread and successful. The eyes of Anomalocaris were particularly impressive, with compound structures containing up to 16,000 individual facets. This gave the creature incredibly sharp vision, allowing it to spot prey from great distances and track their movements with deadly precision. Even after fish evolved and began to dominate marine ecosystems, Anomalocaris and its relatives remained among the largest creatures in the oceans for millions of years. While all of these bizarre invertebrates were duking it out in the Cambrian seas, something even more significant was happening in the background. The first vertebrates, the group that would eventually give rise to fish, amphibians, reptiles, birds, and mammals, were making their humble debut. One of the earliest known vertebrates was Picaia, a creature that looked remarkably like a modern eel. About the size of a paperclip, Picaia didn't have a true skeleton, but rather a notochord, a flexible rod of cartilage that ran along its body like a primitive spinal column. This simple structure was the evolutionary foundation upon which all future vertebrates would be built. Picaia moved through the water by undulating its body in wave-like motions, powered by about 100 small muscle packets called myomeres. The contents of fossilized specimens show that it fed by grazing along the sea floor, scooping up mud and extracting nutrients from it. While this might not sound particularly impressive, the presence of muscles, nerves, and blood vessels in Picaia suggests that it was already well on its way to becoming a true vertebrate. Even more primitive was Milocunmingia, a creature so small that its body didn't exceed the size of a paperclip. Found in rocks from southern China, this tiny animal already showed many of the features that would define vertebrates: fins, muscles, a skull, and even gills. Many researchers consider it to be the very first known vertebrate, making it the ancestor of every backboned animal that has ever lived. As dramatic as the Cambrian explosion was, it was just the opening act for an even more spectacular show. The Ordovician period, which began about 485 million years ago, saw an even greater diversification of life forms, as creatures continued to evolve into increasingly complex and terrifying forms. This period marked the greatest continental fragmentation in Earth's history, with land masses breaking apart and drifting to new positions around the globe. The closure of some oceans and the opening of others created new evolutionary pressures and opportunities, leading to another explosion of biological diversity. The fossil record from the Ordovician shows an incredible increase in the number of deep water species, along with the first truly pelagic animals that spent their entire lives swimming in the open ocean. Predators became better equipped to catch their prey, while prey species developed increasingly sophisticated defenses. The evolutionary arms race that had begun in the Cambrian was now escalating to new levels of intensity. Coral reefs built by sponges and other creatures grew and multiplied, providing shelter for an incredible diversity of animals. At the same time, some creatures were taking their first tentative steps onto land, leaving footprints on ancient shores that we can still see today in the fossil record. Among the most successful predators of the Ordovician period were the nautiloids, relatives of modern squids and octopuses that developed some of the most sophisticated hunting strategies ever seen in the ancient oceans. These creatures proved their dominance by fossils found in rocks around the world, showing that they had successfully colonized every major ocean basin. The early nautiloids were probably planktivores that moved up and down in the water column by filling chambers in their shells with gas and then emptying them again. This allowed them to control their buoyancy with remarkable precision, rising to the surface to feed and then sinking back to the depths to avoid predators or harsh conditions. As nautiloids evolved, they developed increasingly sophisticated methods of locomotion and hunting. They learned to move by projecting jets of water through holes near their heads, giving them the ability to dart through the water with sudden bursts of speed. Their tentacles became more dexterous and powerful, allowing them to capture prey and bring it to their hard parrot-like beaks. While most nautiloids had shells only about 4 inches long, some species grew to truly monstrous proportions. The largest specimens could reach lengths of up to 20 feet, making them some of the biggest predators that have ever lived in Earth's oceans. At the time, these giant nautiloids sat firmly at the top of the aquatic food chain, with few creatures large enough or powerful enough to challenge them. Evidence from damaged fossil shells suggests that nautiloids frequently attacked each other, engaging in battles that must have been absolutely spectacular to witness. Some fossils even preserve traces of color patterns that suggest certain species used camouflage to ambush their prey, with gray and brown bands that would have allowed them to blend into the dark waters of the ancient seas. While nautiloids were perfecting their hunting techniques, another group of creatures was developing innovations that would change the course of evolution forever. The first vertebrates with complete skeletons were appearing in the fossil record, and many of them were covered in armor that would have made a medieval knight jealous. One of the most impressive of these early armored fish was Sacabambaspis, a creature that looked like a giant tadpole wearing a helmet. Growing up to 10 inches in length, this fish had bony shields covering the top and bottom of its head, probably to protect it from the large invertebrate predators that still dominated the seas. The rest of Sacabambaspis' body was covered with long overlapping scales that provided additional protection. It had no jaws and had to feed by sucking up food from the bottom of the water and then crushing it in its throat. Its eyes were positioned between 2 small nostrils, and its mouth was armed with thin plates that helped it process its food. Some fossils of Sacabambaspis show scratches on their bellies, evidence that these creatures spent much of their time scraping along the seafloor in search of food. While this might seem like a humble lifestyle, these armored fish were actually pioneers that were experimenting with new ways of living that would eventually lead to the incredible diversity of vertebrates we see today. But not all of the Ordovician predators were vertebrates. Some of the most terrifying creatures of this period were arthropods that had evolved into forms that would give anyone nightmares. The Eurypterids, also known as sea scorpions, included some of the largest predators that have ever lived. Pterygotus anglicus, whose name means winged fish, could reach lengths of up to 6 feet, making it one of the most formidable predators of its time. Despite its name, this creature wasn't a fish at all, but rather a giant arthropod related to modern scorpions and spiders. Its body was built for speed and efficiency, with 4 pairs of legs for walking and a 5th pair that looked more like flippers for swimming. The most terrifying feature of Pterygotus was its massive claws, which were perfect for seizing and crushing prey. Its eyesight was probably excellent, with a pair of gigantic compound eyes on the sides of its head and a 2nd pair of smaller eyes in the center. This gave it nearly 360-degree vision, making it almost impossible for prey to escape its notice. The body of Pterygotus was perfectly adapted for life as an aquatic predator. Its flat tail probably functioned as a fin, providing propulsion and steering as it hunted through the ancient seas. Despite its fearsome appearance and impressive size, even Pterygotus would eventually fall victim to the catastrophic mass extinction that ended the Ordovician period. While all of these aquatic dramas were playing out in the oceans, something equally significant was happening along the shorelines of the ancient world. The first animals were beginning to venture out of the water and onto land, taking the first tentative steps in what would become one of the most important transitions in the history of life. The earliest land animals were probably Eurypterids, the same group that included the giant sea scorpions. These arthropods had external skeletons that could support their weight out of water, pointed tails for defense, and articulated bodies with multiple pairs of legs that could carry them across dry land. About the size of large shrimp, these pioneer land animals looked like a cross between a lobster and a pillbug. They probably ventured onto land during low tide to feed on the bacteria and microbes that lined the shorelines, taking advantage of a food source that was literally served up on a platter for any creature brave enough to leave the safety of the water. But venturing onto land wasn't just about finding new food sources. It was also about escaping the increasingly dangerous marine environment. With giant nautiloids and sea scorpions patrolling the waters, the shoreline might have seemed like a safe haven where smaller creatures could feed and reproduce without constantly looking over their shoulders for predators. All of this incredible diversity and evolutionary experimentation came to a sudden and catastrophic end about 445 million years ago. The Ordovician mass extinction was one of the most severe in Earth's history, wiping out an estimated 85% of all existing species in what can only be described as a planetary catastrophe. The extinction particularly affected bottom-dwelling organisms like trilobites, echinoderms, and brachiopods, as well as free-swimming creatures like nautiloids. Entire ecosystems that had taken millions of years to develop were destroyed in what was, geologically speaking, the blink of an eye. The cause of this mass extinction was a combination of factors that created a perfect storm of environmental destruction. A massive ice age had begun, with the South Pole located over what is now North Africa. A huge ice cap, twice the size of the current Antarctic ice sheet, covered much of the southern supercontinent of Gondwana. As water became locked up in ice, sea levels dropped by over 160 feet, drying out the shallow seas where most marine life flourished. But the problems didn't stop there. The oceans also experienced what scientists call an anoxic event, where oxygen levels dropped to dangerously low levels, suffocating marine life on a global scale. What had once been oceans teeming with life became oceans of desolation. The crisis lasted for 1 to 2 million years, long enough to completely reshape the biological landscape of our planet. When life finally began to recover, it would take new forms and follow new evolutionary paths, setting the stage for the next chapter in Earth's terrifying prehistory. The world we've explored today represents just a fraction of the incredible story that unfolded before the dinosaurs ever appeared. We've witnessed the birth of complex life, the first evolutionary arms races, and catastrophic extinctions that nearly ended everything. But what we've seen is still just the beginning of this incredible journey. Through deep time, in the next installment of this series, we'll venture into even more dangerous territory as we explore the rise of the first jawed predators, creatures that would make everything we've encountered today look like harmless minnows. We'll witness the evolution of armor that could withstand crushing bites, the development of weapons that could slice through the toughest defenses, and mass extinctions that make the Ordovician crisis look like a minor setback. If you're fascinated by these glimpses into Earth's terrifying past, make sure to smash that like button and subscribe with notifications turned on. The prehistoric world holds secrets that will completely change how you see life on our planet, and we're just getting started on this incredible journey. Drop a comment below and let me know which of these ancient creatures surprised you the most. Were you more terrified by the five-eyed opabinia or the giant sea scorpions? And remember, the most nightmarish chapters of Earth's prehistory are still ahead of us. Trust me, you won't want to miss what's coming next. The recovery from the Ordovician mass extinction set the stage for one of the most revolutionary developments in the history of life on Earth. As the ice caps melted and sea levels rose again, creating vast shallow seas across the continental shelves, something extraordinary was about to happen that would forever change the balance of power in the ancient oceans. About 4.4 million years ago, the Silurian period began, and with it came the dawn of a new era. This wasn't just another chapter in the story of life. This was the beginning of the age of fishes, and more terrifyingly, the age of jaws. For the first time in Earth's history, creatures were evolving the ability to bite with devastating force, transforming the oceans into battlegrounds more brutal than anything we've witnessed so far. The continental configuration during this period was unlike anything we see today. After the closure of ancient oceans, massive land masses had welded together to form what geologists call the Old Red Sandstone Continent. But it was in the warming seas surrounding these land masses that the real action was taking place. Coral reefs were exploding in size and diversity, creating complex three-dimensional habitats that could support an incredible variety of life forms. But here's what makes this period truly terrifying from our perspective. This was when the first true arms race between predator and prey began in earnest. The creatures that emerged from this evolutionary battlefield would be unlike anything that had come before, armed with weapons and defenses that seem almost too advanced for their time. The most significant evolutionary development of the Silurian period was the appearance of jaws, formed from what had once been simple gill supports. This might seem like a minor anatomical change, but it represented a revolution in predatory capability that would reshape every ecosystem on the planet. The first jawed vertebrates came in two distinct varieties, each terrifying in its own way. The acanthodians, known as spiny sharks, were covered in sharp, bony spines that projected from their fins like organic swords. These weren't just for show. The spines were weapons, designed to inflict maximum damage on anything that tried to attack them. But even more formidable were the placoderms, whose name literally means plate-skinned. These creatures took the concept of armor to a whole new level, encasing the front part of their bodies in bony plates that were virtually impenetrable. This wasn't just protection, it was a statement of intent, a declaration that these creatures were built for war. The placoderms were among the first vertebrates to develop movable jaws and teeth, innovations that would prove to be game changers in the evolutionary arms race. They were also among the first creatures to develop paired fins, a feature that would eventually evolve into the limbs that allowed vertebrates to conquer the land. But perhaps most remarkably, some placoderms were among the first vertebrates to give birth to live young rather than laying eggs. Fossilized specimens found in Western Australia contain the remains of embryos, providing clear evidence that these ancient predators were already experimenting with advanced reproductive strategies over 380 million years ago. The armor that covered placoderms wasn't just thick. It was sophisticated, engineered to withstand the most powerful attacks that the ancient seas could deliver. The bony plates that covered their heads and upper bodies were proof that the Silurian seas were a merciless environment where creatures literally devoured each other on a daily basis. But the most terrifying aspect of placoderm armor wasn't its defensive capabilities. It was what it implied about the threats these creatures were facing. The fact that they needed such heavy protection suggests that the ancient oceans were filled with predators capable of delivering crushing bites and devastating attacks. The placoderms themselves were no innocent victims. They were active predators that lurked on the seafloor, waiting for prey to come within striking distance. Their jaws were capable of exerting tremendous force, and their teeth were designed to slice through the toughest defenses that their prey could muster. Some placoderms grew to truly monstrous proportions. Dunkla austeus, which we'll encounter in detail later, could reach lengths of up to 20 feet and possessed jaws capable of exerting a crushing force of over 100 pounds per square inch. To put that in perspective, that's more than twice the bite force of a great white shark and comparable to the bite of a Tyrannosaurus rex. But not all placoderms were active predators. Some, like Titanic, grew to lengths of over 25 feet and weights of more than a ton, but they had no teeth at all. Instead, they were filter feeders that cruised through the ancient seas with their mouths wide open, straining plankton and small organisms from the water like living whale sharks. While the placoderms were developing their armored approach to survival, the acanthodians were taking a different evolutionary path. These creatures, which appeared about 400 million years ago, were characterized by the long, sharp spines that projected from their fins like organic daggers. The spines of acanthodians weren't just defensive weapons. They were also used for display, intimidation, and potentially even as tools for manipulating their environment. Some species had spines that were elaborately decorated with ridges, grooves, and other ornamental features that would have made them stand out in the ancient seas. The bodies of acanthodians were covered with tiny diamond-shaped scales that gave them a distinctly shark-like appearance. Like modern sharks, they had heterocircled tails, meaning that the upper lobe was longer than the lower lobe. This tail design was perfectly adapted for rapid acceleration and agile maneuvering, making acanthodians formidable pursuit predators. Some acanthodians were indeed active predators with large eyes for spotting prey and sharp teeth for capturing it. But others had no teeth at all and were content to filter small organisms from the water. This diversity of feeding strategies allowed acanthodians to exploit a wide range of ecological niches, making them one of the most successful groups of early vertebrates. The acanthodians flourished for over 150 million years, colonizing both marine and freshwater environments around the world. But eventually, they were outcompeted by more advanced groups of fish and became extinct during the Permian period, about 250 million years ago. While these aquatic dramas were playing out in the oceans, something equally momentous was happening on land. The invasion of the continents by complex life forms was accelerating, with both plants and animals making increasingly bold forays into terrestrial environments. The first large plants to colonize the land were primitive vascular plants called Cooksonia. These simple organisms might not look like much to modern eyes, but they represented a revolutionary step in the evolution of life on Earth. Unlike the bacteria and algae that had previously dominated terrestrial environments, Cooksonia had developed sophisticated systems for transporting water and nutrients throughout their bodies. The size of Cooksonia varied dramatically, from tiny specimens just a few centimeters tall to giants that reached heights of over 3 feet. Their microscopic analysis reveals a functional vascular system that allowed them to transport water from the soil through their stems, ensuring a constant supply of moisture even during dry periods. But perhaps most importantly, Cooksonia fossils show evidence of stomata, tiny holes in their surface that allowed for gas exchange with the atmosphere. This was their respiratory system, and without it, they never would have been able to survive in the harsh terrestrial environment. The stems of Cooksonia ended in trumpet-shaped structures called sporangia, which were used to release spores that could travel great distances to colonize new areas. These small plants dominated the continents for over 40 million years, serving as the foundation upon which all future terrestrial ecosystems would be built. Following closely behind the plants came the first animals to make the transition from water to land. The best candidates for the title of pioneering land animals were the ancestors of modern millipedes and centipedes, arthropods that had evolved the ability to breathe air and support their own weight on dry land. One of the earliest known terrestrial animals was Pneumodesmus, a creature that measured just over 2 centimeters in length, but represented a monumental step in evolutionary history. This small arthropod had up to 40 pairs of legs, giving it the stability it needed to move across uneven terrain. The most telling evidence that Pneumodesmus lived on land comes from the spiracles, small holes running along its body that allowed it to breathe air directly. These respiratory openings are clear proof that this creature had made the full transition from aquatic to terrestrial life, becoming one of the first animals to breathe the atmosphere of our planet. The large, claw-like appendages at the front of Pneumodesmus's body were probably used for both defense and offense. These could have posed a serious threat to smaller creatures, making this pioneering land animal one of the first terrestrial predators in Earth's history. The vegetation that these early land animals encountered was unlike anything that exists today. Primitive plants like Cooksonia created landscapes that were both alien and hostile, with little protection from the harsh conditions that prevailed on the early continents. But for creatures brave enough to make the transition, the land offered new opportunities and new resources that were completely untapped by marine life. The Devonian period, which began about 419 million years ago, marked the beginning of what many paleontologists consider to be the most important transition in the history of vertebrate evolution. This was when fish began their transformation into tetrapods, 4-limbed animals that would eventually give rise to amphibians, reptiles, birds, and mammals. The Devonian world was dramatically different from anything that had come before. The breakup of ancient ocean basins and the collision of continents created a paleogeographic configuration that was unlike anything in Earth's previous history. The first forests were becoming established in equatorial regions, participating in photosynthetic processes that were beginning to build up the ozone layer that would eventually protect life from harmful ultraviolet radiation. The climate during the early Devonian was uniformly warm, creating ideal conditions for the development of massive reef systems. These reefs weren't built by the corals we're familiar with today, but by ancient organisms that created complex three-dimensional structures that provided shelter and resources for an incredible diversity of life forms. But the most significant development of the Devonian period was the evolution of fish with fleshy fins, the group that would eventually give rise to all land-dwelling vertebrates. These creatures were experimenting with new ways of moving and breathing that would eventually allow them to leave the water entirely and colonize the terrestrial environment. Among the most important fish of the Devonian period were the sarcopterygians, or lobe-finned fish, which developed some of the most sophisticated adaptations for life in shallow water and potentially on land. These creatures had fleshy fins that were supported by robust bones, giving them the strength and flexibility needed to move in environments where other fish would be helpless. One of the most remarkable of these early lobe-finned fish was Eusthenopteron, a creature that could have been a pioneer in the conquest of dry land. It had a pair of pelvic fins and a pair of pectoral fins, each connected to the body by a single bone that was remarkably similar to the bones found in the limbs of land-dwelling vertebrates. In these advanced fish, the swim bladder had been modified to function as a primitive lung, allowing them to breathe air when necessary. Their bony fins were strong enough to support their weight, enabling them to crawl along the bottom of shallow pools and even venture onto land for short periods. All evidence suggests that Eusthenopteron could reach lengths of up to 6 feet, making it a formidable predator in the shallow waters and swamps where it lived. However, most paleontologists agree that it never made the full transition to terrestrial life, remaining primarily aquatic throughout its existence. The search for the transitional forms between fish and tetrapods has been one of the most exciting areas of paleontological research in recent decades. One of the most important discoveries in this field was Tiktaalik, a creature that seems to bridge the gap between aquatic and terrestrial life. Tiktaalik was discovered on Ellesmere Island in the Canadian Arctic archipelago, in rocks that date to about 375 million years ago. This remarkable creature could reach lengths of up to 8 feet and possessed a combination of features that were both fish-like and tetrapod-like. The most striking feature of Tiktaalik was its flattened head, which was capable of turning thanks to a mobile neck. This was a crucial adaptation for life in shallow water, where the ability to look around without moving the entire body would have been a significant advantage. Small holes in the skull that could be interpreted as nostrils suggest that Tiktaalik might have been capable of breathing air, at least to some extent. The fins of Tiktaalik were supported by robust bones and joints that were comparable to those found in the wrists of land animals. These powerful appendages could have been used for paddling through water, but they were also strong enough to support the creature's weight on land, allowing it to move across mud flats and shallow areas. From impressions left in the rocks where its fossils were found, scientists have determined that Tiktaalik probably didn't spend extended periods out of water, but its adaptations suggest that it was well on its way to making the full transition to terrestrial life, representing a crucial step in the evolution of land vertebrates. The transition from fish to tetrapods involves solving two fundamental problems: how to breathe air efficiently and how to move on land without the buoyant support of water. The creatures that accomplished this transition were among the most important animals in the history of life on Earth. Two of the oldest known tetrapods, Acanthostega and Ichthyostega, provide crucial insights into how this transition occurred. These creatures lived about 365 million years ago and represent some of the earliest experiments in tetrapod body design. Acanthostega was about 2 feet long and had a flat head gills for breathing in water, and a large tail fin that was ideal for swimming. But it also had lungs that allowed it to breathe air at the surface, and 4 limbs that ended in 8 toes each. However, the lack of proper joints in its limbs suggests that it probably couldn't support its own weight on land. Ichthyostega was larger, reaching lengths of over 3 feet, and appears to have been better adapted for life on land. Its ribs were more robust, and its 7-fingered limbs were stronger and more capable of supporting weight. However, it still retained many fish-like features, including gills and a powerful tail fin. These early tetrapods probably spent most of their time in water, using their limbs to paddle through vegetation in search of prey. But they represented crucial steps in the evolution of land vertebrates, experimenting with new ways of moving and breathing that would eventually allow their descendants to colonize terrestrial environments permanently. The incredible diversity and evolutionary experimentation of the Devonian period came to a catastrophic end about 375 million years ago, when the planet was struck by one of the most severe mass extinctions in its history. Unlike the relatively quick extinction that ended the Ordovician period, the Devonian mass extinction was a prolonged crisis that unfolded over several million years. The causes of this extinction were complex and multifaceted, involving a combination of climate change, ocean chemistry changes, and potentially even extraterrestrial impacts. Massive volcanic eruptions in what is now Siberia released enormous quantities of toxic gases into the atmosphere, poisoning both terrestrial and marine ecosystems. The oceans experienced severe oxygen depletion, creating vast dead zones where marine life simply couldn't survive. Temperatures soared to over 86 degrees Fahrenheit at the equator, creating conditions that were lethal for many forms of life. The lack of oxygen in seawater destabilized marine ecosystems, turning once thriving ocean communities into underwater graveyards. The effects on land were equally devastating. The volcanic eruptions released toxic metals like silver, gold, chromium, iron, and magnesium into the atmosphere, where they were carried by winds and deposited across the globe. These metals gradually poisoned plant life, which began to decline dramatically. As plants died, they released their stored carbon into the atmosphere, creating a runaway greenhouse effect that made the climate crisis even worse. The disappearance of plants then cascaded through the food chain, affecting first herbivores and then carnivores in a chain reaction of ecological collapse. Despite the severity of the Devonian mass extinction, life proved remarkably resilient. The crisis eliminated between 50 and 70% of all species on Earth, but those that survived were often better adapted to the new conditions that emerged in the aftermath of the catastrophe. The extinction particularly affected marine life, with many groups of fish, invertebrates, and other organisms disappearing entirely. But some lineages not only survived, but thrived in the post-extinction world, setting the stage for new evolutionary radiations that would reshape the biological landscape of our planet. Among the survivors were the early tetrapods, which had developed the ability to breathe air and move on land. These adaptations, which had initially evolved for life in shallow water, proved to be crucial for surviving the oxygen-depleted conditions that characterized the extinction event. The plants that survived the crisis were often those that had developed sophisticated root systems and other adaptations for surviving in harsh conditions. These survivor species became the foundation for the recovery of terrestrial ecosystems, gradually rebuilding the complex food webs that had been destroyed by the extinction. The recovery from the Devonian mass extinction set the stage for one of the most remarkable periods in Earth's history. The Carboniferous period, which began about 359 million years ago, would see the rise of vast tropical forests, gigantic arthropods, and the first reptiles. The continental configuration during the Carboniferous was dominated by two major landmasses, Laurussia in the north and Gondwana in the south. These continents were gradually moving toward each other, setting the stage for the formation of the supercontinent Pangaea. The collision of these continental masses caused global sea levels to rise dramatically, flooding large areas of the continents and creating vast shallow seas. More importantly, the movement of the continents created the perfect conditions for the formation of coal, as vast swamps and forests were repeatedly flooded and buried. The climate during the Carboniferous was warm and humid, creating ideal conditions for plant growth. Oxygen levels in the atmosphere climbed to unprecedented heights, reaching 35% compared to the 21% we experience today. This oxygen-rich atmosphere would have profound effects on the evolution of life, allowing some organisms to grow to sizes that would be impossible in today's world. The masters of the Carboniferous forests were unlike any plants that exist today. These were not the flowering plants or even the conifers that we're familiar with, but rather giant versions of more primitive plant groups that had evolved to take advantage of the warm, humid conditions. The most impressive of these forest giants was Lepidodendron, a tree that could reach heights of over 100 feet, with trunks that were more than 3 feet in diameter. These massive plants grew rapidly upward in a single unbranched shoot until they reached the forest canopy, where they would finally branch out into a crown of smaller branches. The tips of these branches carried cone-like structures that contained spores, the reproductive units that would spread to create new forests. When these giant trees died, they would often fall into the swamps where they grew, becoming buried in sediment and eventually transforming into the coal deposits that we mine today. Another important plant from the Carboniferous forests was Glossopteris, found in rocks from South America, Southern Africa, Madagascar, India, and Australia. Despite being one of the main components of coal deposits, relatively little is known about this plant. It was woody and could reach diameters of over 2.5 feet, suggesting that it might have grown to heights similar to Lepidodendron. The high oxygen levels of the Carboniferous atmosphere had a profound effect on arthropod evolution, allowing these creatures to grow to sizes that would be impossible in today's world. The result was an ecosystem dominated by giant insects, spiders, and other arthropods that would seem like monsters to modern eyes. Dragonflies during this period could reach wingspans of over 2 feet, making them comparable in size to modern hawks or eagles. These aerial predators patrolled the skies above the Carboniferous forests, hunting smaller insects with their incredibly acute vision and lightning-fast reflexes. Cockroaches grew to the size of mice, scuttling through the forest undergrowth in search of food. Scorpions reached lengths of over 20 inches, armed with powerful claws and venomous stingers that could take down prey much larger than themselves. But the champion of Carboniferous gigantism was Arthropleura, a creature that holds the record as the largest land arthropod that has ever existed. Although no complete fossils have been found, scientists estimate that this monster could have reached lengths of over 6 feet and widths of nearly 2 feet. Arthropleura was a relative of modern millipedes, covered in a thick carapace made of chitin plates that provided protection from predators. It lived in the tropical swamps that dominated the Carboniferous landscape, feeding on the abundant plant material that carpeted the forest floor. The reason for these giant sizes was the high oxygen content of the Carboniferous atmosphere. Arthropods breathe through a system of tubes called tracheae, which become less efficient as body size increases. But in the oxygen-rich atmosphere of the Carboniferous, these respiratory systems could support much larger body sizes than would be possible today. While giant arthropods dominated the Carboniferous forests, an even more significant evolutionary development was taking place in the background. The first reptiles were evolving from their amphibian ancestors, developing adaptations that would eventually allow them to completely colonize terrestrial environments. The oldest known reptile was Hylonomus, a small creature about 10 inches long that lived in the hollow stumps of giant trees. The fact that these animals were found far from water sources is clear evidence that they had evolved the ability to live their entire lives on land, free from the aquatic constraints that still limited their amphibian relatives. Hylonomus and its relatives had developed the amniotic egg, a revolutionary adaptation that allowed them to reproduce on land without returning to water. This egg contained all the resources needed for embryonic development, including food stores and protective membranes that prevented the developing animal from drying out. The evolution of the amniotic egg was one of the most important innovations in the history of life, allowing vertebrates to finally break free from their aquatic origins and colonize terrestrial environments permanently. This adaptation would eventually lead to the incredible diversity of reptiles, birds, and mammals that have dominated terrestrial ecosystems for the past 300 million years. The journey we've taken today through the Silurian, Devonian, and Carboniferous periods has revealed a world that was simultaneously beautiful and terrifying. A planet where evolutionary innovations were creating new forms of life at an unprecedented pace. We've witnessed the birth of jaws, the first steps onto land, and the rise of giants that would dwarf anything in today's world. But what we've seen is still just a fraction of the incredible story that unfolded before the dinosaurs appeared. The mass extinctions, evolutionary arms races, and ecological revolutions that we've encountered represent some of the most important events in the history of life on Earth. But they're also just the beginning of an even more dramatic story. In the next part of this series, we'll venture into the Permian period, where we'll encounter some of the most bizarre and terrifying creatures that have ever lived. We'll witness the formation of the supercontinent Pangaea, explore ecosystems dominated by sailback predators, and experience the most catastrophic mass extinction in Earth's history, an event so severe that it nearly ended life on our planet entirely. The creatures we'll meet in the next episode make everything we've seen today look tame by comparison. We're talking about predators that could crush bone with their jaws, herbivores the size of elephants, and evolutionary experiments that produced animals so strange they seem like they belong in an alien world. If you're fascinated by these glimpses into Earth's incredible past, smash that like button and subscribe with notifications turned on. The prehistoric world still has secrets that will blow your mind, and we're just getting started on this amazing journey through deep time. Drop a comment below and let me know which of these ancient creatures impressed you the most. Were you more amazed by the giant arthropods of the Carboniferous, or the first steps that fish took onto land? And remember, the most incredible chapters of Earth's prehistory are still ahead of us. Trust me, you definitely don't want to miss what's coming next. As the lush Carboniferous forests began to wither and die, our planet was about to enter what many scientists consider the most alien and terrifying period in its entire history. The Permian period, beginning around 295 million years ago, would last for approximately 50 million years and would witness evolutionary experiments so bizarre that they seem like they were designed by a committee of mad scientists. Picture a world where the familiar green landscapes of the Carboniferous were replaced by vast, scorching deserts that stretched from horizon to horizon. The continental masses that had been scattered across the globe were slowly grinding together like massive tectonic bulldozers, creating mountain ranges that scraped the sky and fundamentally altering the planet's climate systems. The formation of the supercontinent Pangaea was nearing completion, and this reunification of land masses would create environmental conditions more extreme than anything our planet had experienced before. Temperatures could vary from freezing to over 100 degrees Fahrenheit in a single day, creating a world where only the most adaptable and resilient creatures could survive. But survival in this harsh new world would require more than just tolerance for extreme temperatures. The creatures that emerged from the Permian evolutionary crucible would be armed with weapons and defenses that make everything we've seen so far look like children's toys. We're talking about predators with sails on their backs that could regulate their body temperature like living solar panels. Amphibians the size of crocodiles with skulls designed for crushing bone. And the first mammal-like reptiles that would eventually give rise to our own lineage. The world of the Permian was dominated by a single massive landmass that geologists call Pangaea, a supercontinent that extended from pole to pole and was surrounded by a single vast ocean called Panthalassa. This geographical configuration created climate conditions that were unlike anything that had existed before or since in Earth's history. The interior of Pangaea was a land of extremes, where vast deserts stretched for thousands of miles without interruption. The absence of large bodies of water meant that there was nothing to moderate the temperature swings, creating conditions where the same location could experience scorching heat during the day and bone-chilling cold at night. The southern portions of Pangaea remained locked in an ice age that had begun during the late Carboniferous period, with glaciers covering vast areas of what would eventually become South America, Africa, India, and Australia. This glaciation would persist for over 80 million years, creating a world where tropical swamps existed within a few hundred miles of massive ice sheets. The contrast between the frozen south and the arid interior created weather patterns that were both unpredictable and extreme. Massive storms would sweep across the continent, bringing brief but intense rainfall to regions that might not see another drop of water for months or even years. These flash floods would carve deep channels through the landscape, creating temporary rivers that would disappear as quickly as they had formed. In this harsh new world, one creature stood out as the undisputed apex predator, a monster so fearsome that it would haunt the nightmares of every other animal that shared its environment. Dimetrodon, whose name means 2 measures of teeth, was a predator that combined the stealth of a crocodile with the killing power of a great white shark. Although Dimetrodon looked superficially like a dinosaur, it actually belonged to a much older group called synapsids, the lineage that would eventually give rise to all mammals, including humans. This makes Dimetrodon one of our most ancient and most terrifying relatives, a creature that represents what our evolutionary lineage was capable of producing when survival required the ultimate in predatory efficiency. The most distinctive feature of Dimetrodon was the enormous sail that rose from its back, supported by long spines that extended upward from its vertebrae. This sail wasn't just for show. It was a sophisticated thermoregulation system that allowed Dimetrodon to control its body temperature with remarkable precision. By angling its sail toward the sun, Dimetrodon could warm up quickly in the morning, giving it a crucial advantage over its cold-blooded prey. By turning the sail away from the sun or seeking shade, it could cool down during the hottest parts of the day. This ability to regulate its body temperature made Dimetrodon one of the most efficient predators that had ever existed. The genus Dimetrodon included about 10 different species, ranging in size from creatures about 2 feet long to monsters that reached lengths of over 15 feet. The largest specimens could weigh over 600 pounds, making them heavier than an adult grizzly bear and far more dangerous. The skull of Dimetrodon was a masterpiece of predatory engineering, designed to deliver devastating bites that could crush bone and tear through the toughest hides. The front of its jaw was armed with massive, pointed canine teeth that could pierce through armor like skin, while the sides of its mouth contained rows of serrated teeth that worked like organic saw blades. The bite force of Dimetrodon was extraordinary, probably capable of exerting pressures that would have made it one of the most powerful predators of its time. Its jaw muscles were massive, giving it the ability to clamp down on prey with enough force to crush skulls and snap bones. But Dimetrodon wasn't just a brute force predator. It was also a sophisticated hunter that used stealth and strategy to capture its prey. Its powerful legs and muscular tail made it capable of sudden bursts of speed, allowing it to ambush prey from concealment or chase down fleeing animals. The hunting strategy of Dimetrodon probably involved a combination of ambush predation and active pursuit. It would lurk in vegetation near water sources, waiting for unsuspecting prey to come within striking distance. When the moment was right, it would explode from cover with lightning speed, using its massive jaws to deliver a killing bite before its prey could react. While Dimetrodon ruled the land, the swamps and rivers of the Permian world were dominated by creatures that were equally terrifying in their own way. The largest of these was Archaeops, an amphibian that reached lengths of over 6 feet and represented the pinnacle of amphibian evolution. Archaeops was built like a living tank, with a massive skull that was broad and flat, perfectly designed for crushing anything that came within range of its powerful jaws. Its mouth was filled with numerous sharp teeth that could slice through flesh and bone with equal ease, making it one of the most formidable predators in the aquatic environments of the Permian. The lifestyle of Archaeops was semi-aquatic, dividing its time between the water and the land. In the water, it was a patient ambush predator that would lie motionless on the bottom, waiting for fish or other aquatic creatures to come within range. On land, it could hunt smaller terrestrial animals, using its powerful legs to pursue prey across the harsh Permian landscape. The skull of Archaeops was particularly impressive, with bone that was thick enough to absorb tremendous impacts. This suggests that these creatures might have engaged in head-to-head combat with each other, using their skulls as battering rams in territorial disputes or mating competitions. But Archaeops faced a significant threat from an even more dangerous predator. Despite its impressive size and formidable defenses, it was still vulnerable to attack from Dimetrodon, which had both the size and the weaponry needed to take down even the largest amphibians. As the Permian period progressed, the extreme climate conditions that characterized this era began to take an increasingly severe toll on the planet's ecosystems. The formation of Pangaea had disrupted ocean currents and weather patterns, creating a world where environmental conditions were becoming more unstable and unpredictable. The interior of the supercontinent was becoming increasingly arid, with vast deserts expanding to cover areas that had once been lush forests. The lack of vegetation meant that there was little to hold soil in place, leading to massive erosion events that stripped away the topsoil and left behind barren badlands. The contrast between the frozen southern regions and the scorching equatorial zones created atmospheric conditions that were unlike anything in Earth's previous history. Massive temperature gradients drove powerful storm systems across the continent, bringing violent weather that could change from calm to catastrophic in a matter of hours. These extreme conditions put enormous pressure on the planet's ecosystems, forcing evolutionary changes that would have profound implications for the future of life on Earth. Creatures that had thrived in the stable conditions of earlier periods found themselves struggling to survive in a world that was becoming increasingly hostile to life. Despite the harsh conditions of the Permian world, this period also witnessed one of the most important evolutionary developments in the history of life on Earth. The synapsids, the group that included Dimetrodon, began to evolve characteristics that would eventually lead to the emergence of true mammals. These mammal-like reptiles, known as therapsids, developed increasingly sophisticated ways of regulating their body temperature, processing food, and caring for their young. Some species began to develop hair-like filaments that helped insulate their bodies, while others evolved more efficient respiratory systems that allowed them to maintain higher activity levels. The skulls of these creatures also began to change in ways that would prove crucial for their descendants. The jaw muscles became more efficient, allowing for more precise control over biting and chewing. The teeth became more specialized, with different types of teeth serving different functions in processing food. Perhaps most importantly, these creatures began to develop more complex social behaviors and parental care strategies. Some species may have been warm-blooded, allowing them to remain active even during the cooler parts of the day, when their cold-blooded competitors were sluggish. In the oceans surrounding Pangaea, life was also undergoing dramatic changes. The Permian seas were home to some of the most spectacular reef systems that have ever existed, built not by corals as we know them today, but by a variety of other organisms that created complex three-dimensional structures. These reefs were dominated by creatures called fusulinids, single-celled organisms that built elaborate shells and lived in massive colonies. These weren't the tiny, simple organisms that we might expect from single-celled creatures. Some fusulinids built shells that were several inches long and incredibly complex in their internal structure. The reefs also hosted a diverse array of brachiopods, crinoids, and other marine invertebrates that created ecosystems of stunning beauty and complexity. These underwater cities provided shelter and resources for countless species, creating some of the most biodiverse environments that have ever existed in Earth's oceans. But these reef systems were also incredibly fragile, dependent on stable ocean chemistry and temperature conditions that were becoming increasingly rare as the Permian period progressed. The same climate changes that were creating harsh conditions on land were also beginning to affect the oceans, setting the stage for the catastrophic events that would soon follow. The Permian oceans were also home to some truly spectacular predators that rivaled anything on land in terms of their size and ferocity. The sharks of this period had evolved into forms that were both familiar and alien, with some species reaching sizes that would make modern great whites look like minnows. These ancient sharks had developed incredibly sophisticated hunting strategies and sensory systems that allowed them to dominate the marine food webs of their time. Some species had teeth that were designed for crushing shellfish and other hard-shelled prey, while others had razor-sharp teeth that could slice through flesh with surgical precision. The diversity of Permian sharks was extraordinary, with species adapted for every conceivable marine environment, from shallow coastal waters to the deepest ocean basins. Some were fast-swimming pursuit predators that could chase down the swiftest prey, while others were patient ambush predators that waited motionless for unsuspecting victims to come within range. But the sharks weren't the only predators in the Permian seas. The oceans were also home to a variety of other creatures that had evolved their own unique approaches to predation, creating marine ecosystems that were both beautiful and terrifying. As the Permian period drew to a close, the extreme conditions that had characterized this era were beginning to push the planet's ecosystems to their breaking point. The climate was becoming increasingly unstable, with temperature swings that were too rapid and too extreme for many species to adapt to. The formation of Pangaea had also created geological conditions that were setting the stage for one of the most catastrophic events in Earth's history. Deep beneath the surface of what is now Siberia, massive amounts of magma were building up pressure, preparing for eruptions that would dwarf anything in recorded human history. The plant communities that had dominated the Carboniferous were in decline, unable to adapt to the increasingly arid conditions that characterized much of Pangaea. As these plants died out, they took with them the complex food webs that had supported the incredible diversity of life that had flourished during earlier periods. The stage was being set for the most severe mass extinction in Earth's history, an event so catastrophic that it would come to be known as the Great Dying. This extinction would eliminate over 90% of marine species and 75% of terrestrial species, bringing the Paleozoic era to a violent and dramatic end. About 252 million years ago, the geological forces that had been building beneath Siberia finally reached a breaking point. The result was a series of volcanic eruptions that were unlike anything in Earth's recorded history, releasing amounts of lava, ash, and toxic gases that would fundamentally alter the planet's climate and ocean chemistry. These weren't ordinary volcanic eruptions. They were flood basalts that poured molten rock across an area of over 770,000 square miles, creating lava flows that were hundreds of feet thick in some places. The eruptions continued for thousands of years, releasing enormous quantities of carbon dioxide, sulfur dioxide, and other greenhouse gases into the atmosphere. The immediate effects of these eruptions were devastating. The ash clouds blocked out the sun, creating a volcanic winter that caused temperatures to plummet across the globe. But as the ash settled and the greenhouse gases accumulated in the atmosphere, the planet began to experience a runaway greenhouse effect that drove temperatures to lethal levels. The oceans began to acidify as they absorbed carbon dioxide from the atmosphere, creating conditions that were toxic to most marine life. Oxygen levels in seawater dropped to dangerously low levels, creating vast dead zones where nothing could survive. The combination of volcanic activity, climate change, and ocean acidification created a perfect storm of environmental destruction that would eliminate more species than any other event in Earth's history. The Permian Triassic extinction, also known as the Great Dying, was so severe that it came close to ending complex life on our planet entirely. Marine ecosystems were particularly hard hit, with an estimated 96% of marine species disappearing forever. The spectacular reef systems that had dominated Permian seas were completely destroyed, leaving behind nothing but barren rock and sediment. The diverse communities of brachiopods, crinoids, and other invertebrates that had thrived for millions of years were reduced to a handful of survivor species. On land, the extinction was equally devastating. An estimated 75% of terrestrial species disappeared, including most of the large predators and herbivores that had dominated Permian ecosystems. The sail-backed predators like Dimetrodon vanished completely, along with the giant amphibians and most of the mammal-like reptiles. The plants that had managed to survive the increasingly harsh conditions of the late Permian were also severely affected. Entire forest ecosystems collapsed, leaving behind landscapes that were virtually devoid of vegetation. The few plants that did survive were often small, hardy species that could tolerate the extreme conditions that now characterized much of the planet. In the aftermath of the Great Dying, Earth was a planet in ruins. The once diverse ecosystems of the Permian had been reduced to a few hardy survivor species that clung to life in the most marginal environments. The oceans were largely empty. The continents were barren, and the atmosphere was still loaded with toxic gases from the Siberian eruptions. But life, as it had done so many times before, proved remarkably resilient. The survivors of the Great Dying began to slowly recolonize the empty ecosystems, evolving new forms and adapting to the changed conditions. This recovery process would take millions of years, but it would eventually lead to the emergence of entirely new groups of organisms. Among the survivors were a few species of mammal-like reptiles that had managed to weather the extinction crisis. These creatures, known as the disaster fauna, would serve as the foundation for the recovery of terrestrial ecosystems. One of these survivors was Lystrosaurus, a herbivorous creature that looked like a cross between a pig and a hippopotamus. Lystrosaurus was incredibly successful in the post-extinction world, spreading across the entire supercontinent of Pangaea and becoming one of the most abundant animals on Earth. Its success was due to its ability to eat a wide variety of plant materials and its tolerance for the harsh environmental conditions that characterized the early Triassic period. The recovery from the Permian Triassic extinction marked the beginning of the Mesozoic era, the age of reptiles that would eventually give rise to the dinosaurs. The early Triassic world was very different from the Permian, with new evolutionary pressures and opportunities that would drive the evolution of entirely new groups of organisms. The survivors of the Great Dying had inherited a planet that was largely empty of competitors, creating opportunities for rapid evolutionary diversification. The groups that had managed to survive the extinction began to radiate into new ecological niches, experimenting with new body plans and lifestyles. Among these early Mesozoic pioneers were the first archosaurs, the group that would eventually give rise to dinosaurs, pterosaurs, and crocodiles. These creatures were initially small and relatively unspecialized, but they possessed key innovations that would eventually allow them to dominate terrestrial ecosystems. The stage was being set for the age of dinosaurs, but that's a story for another time. The creatures that would rule the Mesozoic world were still millions of years in the future, waiting for the right conditions to emerge and begin their own incredible evolutionary journey. The journey we've taken through the Permian period has revealed a world that was both magnificent and terrifying, a planet where evolutionary experiments created creatures that seem almost too bizarre to be real. We've witnessed the rise of sail-backed predators, the dominance of giant amphibians, and the emergence of the first mammal-like reptiles that would eventually give rise to our own lineage. But we've also seen how this incredible diversity was nearly wiped out entirely by the most catastrophic mass extinction in Earth's history. The Great Dying came closer than any other event to ending complex life on our planet, reducing the incredible biological richness of the Permian to a handful of survivor species. The story of the Permian period is ultimately a story about resilience and recovery. Despite facing environmental challenges that would seem insurmountable, life found a way to survive and eventually flourish again. The survivors of the Great Dying would go on to found new evolutionary lineages that would dominate the planet for the next 250 million years. In our final episode of this series, we'll explore the early Triassic recovery and the emergence of the first dinosaurs. We'll see how the survivors of the Great Dying gave rise to entirely new groups of organisms, and how the stage was set for the age of reptiles that would follow. If you've been amazed by this incredible journey through Earth's most terrifying prehistory, make sure to smash that like button and subscribe with notifications turned on. The story of life on our planet is filled with drama, tragedy, and triumph on a scale that dwarfs anything in human history. And we're just getting started. Drop a comment below and let me know which aspect of the Permian period surprised you the most. Were you more fascinated by the sail-backed predators like Dimetrodon, or were you more shocked by the scale of the Great Dying? And remember, the most incredible chapter of this story is still to come as we explore how life recovered from the brink of extinction and gave rise to the dinosaurs that would rule the world for over 160 million years. But the real monsters of the Carboniferous period weren't the predators we might expect. They were the arthropods, creatures that had evolved to take advantage of the oxygen-rich atmosphere in ways that would be impossible in today's world. The air during this period contained 35% oxygen compared to our modern 21%. And this supercharged atmosphere allowed insects and their relatives to grow to absolutely staggering proportions. Picture dragonflies with wingspans that rivaled modern hawks, soaring through the humid air above vast swamps with the precision of fighter jets. These aerial predators, known as Meganeura, had wingspans that could reach over 2 feet and bodies that stretched nearly a foot in length. Their compound eyes were massive, giving them the ability to spot prey from incredible distances and track multiple targets simultaneously. But even these giant dragonflies paled in comparison to the true champion of Carboniferous gigantism. Arthropleura was a creature so massive that it holds the record as the largest land arthropod that has ever existed on our planet. Although complete fossils have never been found, scientists have pieced together evidence from fragments and trace fossils to estimate that this monster could have reached lengths of over 6 feet and widths of nearly 2 feet. Imagine encountering this creature in the dim light of a Carboniferous forest. Arthropleura was essentially a giant millipede, but one that was covered in thick, overlapping plates of chitin that gave it the appearance of a living tank. Its numerous legs would have carried it through the forest undergrowth with surprising speed, and its massive size would have made it virtually immune to predation from anything else that lived during its time. The diet of Arthropleura appears to have been herbivorous, based on fossilized droppings that contain plant spores and other vegetable matter. But the sheer size of this creature would have made it a formidable presence in any ecosystem, capable of bulldozing through vegetation and potentially crushing smaller animals that got in its way. While giant arthropods dominated the forest floor, the swamps and rivers of the Carboniferous were home to some of the most bizarre amphibians that have ever existed. These creatures were conducting evolutionary experiments that would seem almost surreal by modern standards, developing body plans and lifestyles that push the boundaries of what we consider possible. One of the most remarkable of these amphibian oddities was discovered in old coal mines near Edinburgh, Scotland. Cressigerinus was a creature that looked like someone had taken a giant tadpole and stretched it to impossible proportions. This monster could reach lengths of over 6 feet, with an enormous skull that made up nearly a quarter of its total body length. What made Cressigerinus particularly unsettling was its lifestyle. Unlike modern amphibians, which typically have well-developed limbs for both swimming and walking, Cressigerinus had tiny, almost vestigial limbs that were completely useless for locomotion on land. Instead, it had evolved to live like a giant aquatic snake, undulating through shallow freshwater environments with surprising grace and speed. The skull of Cressigerinus was a masterpiece of predatory design, with a flexible jaw structure that was remarkably similar to that of modern snakes. This allowed the creature to open its mouth incredibly wide, enabling it to swallow prey that was much larger than its head. The inside of its mouth was lined with numerous sharp teeth, including several fangs that could deliver devastating bites to struggling prey. But perhaps the most disturbing aspect of Cressigerinus was its hunting strategy. This creature was an ambush predator that would lie motionless in murky water, waiting for unsuspecting fish or other aquatic animals to come within striking distance. When prey approached, it would explode into motion with lightning speed, using its flexible spine to lunge forward and engulf its victim in a single devastating bite. Even more bizarre was another amphibian from the Carboniferous swamps, a creature so strange that paleontologists initially thought they were looking at some kind of fossilized frisbee. Diplocalus had a skull that was flattened into a perfect disc shape, with 2 horn-like projections extending from the back of its head like the wings of a boomerang. The skull of Diplocalus measured nearly 8 inches across, but was only about 2 inches thick, giving it an appearance that was both comical and deeply unsettling. The eye sockets were positioned very close together on the top of the skull, suggesting that this creature spent most of its time looking upward, probably watching for prey or predators approaching from above. The most puzzling aspect of Diplocalus was its feeding strategy. Its mouth was filled with tiny, needle-like teeth, but it had no fangs or other obvious predatory adaptations. The lower jaw was equipped with small bristles that suggest it was a filter feeder, probably straining small invertebrates and organic particles from the water. Scientists believe that Diplocalus would position itself on the bottom of shallow pools with its disc-shaped head angled upward, creating a living trap for small creatures that swam too close. The bizarre shape of its skull might have helped it blend in with rocks and other debris on the bottom, making it nearly invisible to both prey and predators. While these amphibian experiments were taking place in the swamps, something far more significant was happening in the drier upland areas of the Carboniferous world. The first true reptiles were evolving, developing innovations that would eventually allow vertebrates to completely conquer terrestrial environments. The discovery of Hylonomus in the hollow stumps of ancient trees in Nova Scotia revealed a creature that had made the full transition from aquatic to terrestrial life. This small reptile, measuring only about 10 inches from nose to tail, might not seem particularly impressive, but it represented one of the most important evolutionary breakthroughs in Earth's history. What made Hylonomus so significant was its development of the amniotic egg, a revolutionary adaptation that freed reptiles from their dependence on water for reproduction. Unlike amphibians, which had to return to water to lay their eggs, reptiles could reproduce anywhere on land, opening up vast new territories for colonization. The amniotic egg was like a portable aquatic environment, containing all the water and nutrients needed for embryonic development. This innovation would eventually lead to the incredible diversity of reptiles, birds, and mammals that have dominated terrestrial ecosystems for the past 300 million years. Hylonomus lived by hunting insects and small arthropods in the Carboniferous forests, using its sharp teeth and quick reflexes to capture prey. Its discovery inside fossilized tree stumps suggests that these early reptiles were already developing complex behaviors, using hollow logs as shelter, and possibly even as nesting sites. The incredible diversity and gigantism of the Carboniferous period couldn't last forever. As the period progressed, the very conditions that had allowed life to flourish began to change in ways that would prove catastrophic for many of the specialized creatures that had evolved during this time. The vast forests that had dominated the Carboniferous landscape were gradually being replaced by more arid environments as the climate began to cool and dry. The formation of the supercontinent Pangaea was disrupting ocean currents and weather patterns, creating conditions that were less favorable for the tropical swamps where so many Carboniferous species had thrived. Most importantly, oxygen levels in the atmosphere began to decline from their Carboniferous peak of 35%. This change had particularly severe effects on the giant arthropods, whose respiratory systems were specifically adapted to the oxygen-rich conditions of the period. As oxygen levels dropped, these creatures found themselves unable to maintain their enormous body sizes. The decline in atmospheric oxygen was gradual but relentless, driven by changes in plant communities and ocean chemistry that reduced the planet's ability to produce and maintain high oxygen concentrations. This environmental shift would eventually lead to the extinction of most of the giant arthropods and force the survivors to evolve smaller body sizes. As the Carboniferous period drew to a close, the stage was being set for an even more dramatic chapter in Earth's history. The environmental changes that had begun during the late Carboniferous were accelerating, creating conditions that would favor entirely different groups of organisms. The amphibians that had dominated Carboniferous ecosystems were finding themselves increasingly at a disadvantage in the drying climate. Their dependence on water for reproduction and their permeable skin made them vulnerable to the increasingly arid conditions that were spreading across the continents. In contrast, the reptiles were thriving in these new conditions. Their scaly skin provided excellent protection against water loss, and their amniotic eggs allowed them to reproduce in environments where amphibians couldn't survive. As the Carboniferous gave way to the Permian, reptiles began to diversify rapidly, filling ecological niches that had previously been occupied by amphibians. The synapsids, the group that would eventually give rise to mammals, were among the most successful of these early reptiles. These creatures were developing increasingly sophisticated adaptations for life in terrestrial environments, including more efficient metabolisms and more complex social behaviors. The Carboniferous period left behind one of the most important legacies in Earth's history. Vast deposits of coal that formed from the remains of the giant forests that dominated this era. When these massive trees died, they often fell into the swamps where they grew, becoming buried in sediment and preserved from decay. Over millions of years, the buried plant material was compressed and heated, gradually transforming into the coal deposits that we mine today. The process of coalification required very specific conditions. The plant material had to be buried quickly to prevent decay, and it had to be subjected to just the right combination of pressure and temperature. The coal deposits that formed during the Carboniferous period represent one of the largest accumulations of organic carbon in Earth's history. These deposits contain the fossilized remains of entire ecosystems, preserving not just the trees themselves, but also the insects, spiders, and other small creatures that lived in the Carboniferous forests. The formation of coal during this period was so extensive that it gave the Carboniferous its name, which literally means coal-bearing. The conditions that allowed for such massive coal formation were unique in Earth's history, requiring the perfect combination of climate, vegetation, and geological conditions that has never been repeated. The Carboniferous forests were unlike anything that exists in today's world. These weren't the familiar deciduous or coniferous forests that we know, but rather strange assemblages of giant club mosses, horsetails, and seed ferns that created landscapes that would seem utterly alien to modern eyes. The dominant trees of these forests were lepidodendrons, massive club mosses that could reach heights of over 130 feet, with trunks that were more than 3 feet in diameter. These giants grew in a completely different way from modern trees, shooting up rapidly in single, unbranched stems until they reached the forest canopy, where they would finally branch out into crowns of smaller branches. The reproduction of these ancient trees was also completely different from modern plants. Instead of flowers or cones, they produced massive sporangia at the tips of their branches, structures that could release millions of spores into the air. When these spores landed in suitable conditions, they would grow into new trees, gradually spreading the forest across the landscape. The understory of Carboniferous forests was dominated by giant ferns and seed ferns, some of which could reach heights of 30 feet or more. These plants created a dense, humid environment that was perfect for the amphibians and arthropods that made these forests their home. The Carboniferous forests were responsible for one of the most dramatic changes in Earth's atmosphere since the origin of life itself. The massive amount of plant material that these forests produced resulted in an enormous increase in atmospheric oxygen, creating conditions that were unlike anything that had existed before or since. The high oxygen levels of the Carboniferous atmosphere had profound effects on the evolution of life. Not only did they allow arthropods to grow to gigantic sizes, but they also affected the physiology and behavior of all air-breathing organisms. The increased oxygen availability would have made it easier for animals to maintain high activity levels and support larger body sizes. But the oxygen-rich atmosphere also created new dangers. The high oxygen content made fires much more likely to ignite and spread, creating forest fires that could burn with incredible intensity. Some scientists believe that the Carboniferous atmosphere was so oxygen-rich that even wet vegetation could burn, creating firestorms that would have been devastating to forest ecosystems. The removal of carbon dioxide from the atmosphere by the growing forests also had significant effects on global climate. The reduction in this greenhouse gas contributed to the cooling that marked the end of the Carboniferous period, helping to trigger the ice ages that would characterize the late Paleozoic. While giant arthropods and bizarre amphibians dominated the Carboniferous landscape, some of the most important evolutionary developments were taking place on a much smaller scale. The forests were home to countless species of insects, spiders, and other small arthropods that were developing increasingly sophisticated hunting strategies and survival techniques. Many of these small predators were experimenting with venom as a hunting tool, developing toxins that could paralyze or kill prey much larger than themselves. The scorpions of the Carboniferous period were particularly impressive, with some species reaching lengths of over 20 inches and possessing stingers that could deliver devastating doses of venom. The spiders of this period were also developing new hunting strategies, including the use of webs to capture flying insects. The high oxygen levels of the Carboniferous atmosphere supported large populations of flying insects, creating abundant prey for web-building spiders. Even the insects themselves were becoming more sophisticated predators. The giant dragonflies that patrolled the Carboniferous skies were equipped with incredibly acute vision and lightning-fast reflexes, allowing them to snatch smaller insects out of the air with remarkable precision. One of the most important developments of the Carboniferous period was the evolution of seed plants, which would eventually come to dominate terrestrial ecosystems. Unlike the spore-producing plants that had dominated earlier periods, seed plants could reproduce more efficiently and colonize new environments more rapidly. The first seed plants were the seed ferns, which looked superficially like modern ferns but reproduced using seeds rather than spores. These plants were more drought-tolerant than their spore-producing relatives, allowing them to colonize drier upland areas that had previously been uninhabitable. The evolution of seeds was a crucial step in the conquest of terrestrial environments by plants. Seeds contained stored food supplies that allowed young plants to establish themselves in harsh conditions, and they could survive periods of drought or cold that would kill spore-producing plants. The success of seed plants during the Carboniferous period set the stage for the even greater success of flowering plants and conifers in later periods. The innovations that first appeared in Carboniferous seed plants would eventually give rise to the diverse plant communities that dominate modern terrestrial ecosystems. As the Carboniferous period drew to a close around 299 million years ago, the unique conditions that had allowed this incredible diversity of life to flourish were coming to an end. The climate was becoming cooler and drier, the oxygen levels were declining, and the vast tropical swamps were being replaced by more arid environments. The giant arthropods that had been the signature creatures of the Carboniferous were among the first to feel the effects of these changes. As oxygen levels dropped, these creatures found themselves unable to maintain their enormous body sizes, and many species became extinct or evolved smaller forms. The amphibians that had dominated Carboniferous ecosystems were also struggling to adapt to the changing conditions. Their dependence on water for reproduction and their permeable skin made them vulnerable to the increasingly dry climate, and many species were forced to retreat to increasingly marginal habitats. But while some groups were declining, others were just beginning their rise to dominance. The reptiles that had first appeared during the Carboniferous were diversifying rapidly, developing new adaptations that would allow them to thrive in the harsh conditions of the coming Permian period. The environmental changes that marked the end of the Carboniferous period were setting the stage for one of the most dramatic chapters in Earth's history. The Permian period would see the evolution of some of the most bizarre and terrifying creatures that have ever existed, including sailback predators, giant amphibians, and the first mammal-like reptiles. The formation of the supercontinent Pangaea was nearing completion, creating climate conditions that would be more extreme than anything Earth had experienced before. The vast interior of this supercontinent would become a scorching desert, while the edges would be subject to violent storms and unpredictable weather patterns. The creatures that would dominate the Permian world were already beginning to evolve during the late Carboniferous, developing the adaptations that would allow them to survive in the harsh conditions that lay ahead. The synapsids in particular were developing increasingly sophisticated mechanisms for temperature regulation and energy conservation. But the Permian period would also see the most catastrophic mass extinction in Earth's history, an event so severe that it would come to be known as the Great Dying. This extinction would eliminate over 90% of marine species and 75% of terrestrial species, bringing the Paleozoic era to a violent end. The Carboniferous period represents one of the most important evolutionary laboratories in Earth's history. a time when life was experimenting with new forms and strategies on an unprecedented scale. The unique environmental conditions of this period allowed for evolutionary experiments that would have been impossible at any other time. The high oxygen levels created opportunities for gigantism that have never been repeated, allowing arthropods to reach sizes that would be impossible in today's atmosphere. The vast tropical forests provided stable environments where complex ecosystems could develop and persist for millions of years. The innovations that first appeared during the Carboniferous period would have profound effects on the future evolution of life on Earth. The amniotic egg, which first evolved in Carboniferous reptiles, would eventually allow vertebrates to completely colonize terrestrial environments. The seed, which first appeared in Carboniferous plants, would revolutionize plant reproduction and allow plants to colonize previously uninhabitable environments. Even the coal deposits that formed during this period would have lasting effects on Earth's history, providing the fossil fuels that would power human civilization millions of years later. The Carboniferous period was truly a time when the foundations of the modern world were being laid. Even though the creatures that lived during this time would seem utterly alien to modern eyes. The incredible journey we've taken through the Carboniferous period has revealed a world that was both beautiful and terrifying, a planet where evolutionary experiments were creating new forms of life at an unprecedented pace. We've witnessed the rise of giant arthropods that dwarfed anything in today's world, explored the bizarre amphibian experiments that pushed the boundaries of what we consider possible, and seen the first tentative steps toward the reptilian revolution that would reshape life on Earth. But what we've discovered is that the Carboniferous period was just one chapter in an even more incredible story. The environmental changes that ended this era were setting the stage for the most dramatic period in Earth's prehistory, a time when life would face its greatest challenges and most spectacular innovations. In the next and final episode of this series, we'll venture into the Permian period, where we'll encounter creatures that make everything we've seen so far look tame by comparison. We'll witness the rise of sail-backed predators like Dimetrodon, explore the world of giant amphibians and early mammal-like reptiles, and experience the most catastrophic mass extinction in Earth's history. The story of life before the dinosaurs is ultimately a story about survival, adaptation, and the incredible resilience of life itself. Despite facing environmental challenges that would seem insurmountable, life found ways to not just survive, but thrive, creating ecosystems of stunning complexity and beauty. If you've been amazed by this journey through Earth's most incredible prehistory, make sure to smash that like button and subscribe with notifications turned on. The story of life on our planet is filled with drama, innovation, and survival on a scale that makes any Hollywood blockbuster look tame by comparison. Drop a comment below and let me know which of these Carboniferous creatures surprised you the most. Were you more impressed by the giant dragonflies soaring through oxygen-rich skies, or the bizarre amphibians conducting their evolutionary experiments in ancient swamps? And remember, the most dramatic chapter of this incredible story is still to come, as we explore the rise and fall of the most alien world that Earth has ever known. As the oxygen-rich atmosphere of the Carboniferous began to thin and the great forests withered into memory, our planet was entering what would become the most alien and nightmarish chapter in its entire history. The Permian period, stretching from 295 to 252 million years ago, would witness the rise of creatures so bizarre and terrifying that they seem like they were designed by evolution's darkest imagination. Picture this: vast deserts stretching endlessly under a merciless sun, where temperatures could swing from scorching heat to bone-chilling cold in a single day. The lush swamps that had defined the Carboniferous were disappearing, replaced by arid wastelands where only the most adaptable and ruthless creatures could survive. This wasn't just another period of geological time. This was evolution's most extreme experiment, a 50-million-year-long trial by fire that would push life to its absolute limits. The continental masses were grinding together like massive tectonic bulldozers, forming the supercontinent Pangaea. This reunification of land masses created climate conditions more extreme than anything our planet had experienced before or since. The interior of this megacontinent became a furnace of scorching deserts, while the coasts were battered by violent storms that could change from calm to catastrophic in hours. But it was the creatures that evolved in this hellish environment that make the Permian truly terrifying. We're talking about sail-backed predators that use their backs like solar panels to regulate their body temperature, giving them deadly advantages over their prey. Giant amphibians with skulls designed for crushing bone roam the remaining waterways like living nightmares. And most significantly, the first mammal-like reptiles were evolving, developing innovations that would eventually lead to our own lineage. The world of the Permian was dominated by Pangaea, a supercontinent that stretched from pole to pole and created environmental conditions that were absolutely unprecedented in Earth's history. This wasn't just a large landmass. It was a geological monster that fundamentally altered the planet's climate, ocean currents, and weather patterns in ways that would have catastrophic consequences for life. The sheer size of Pangaea meant that vast areas of the continental interior were thousands of miles from the nearest ocean. Without large bodies of water to moderate temperatures, these regions became scorching deserts during the day and frozen wastelands at night. Temperature swings of 60 degrees Fahrenheit or more in a single day were common, creating conditions that would challenge even the most adaptable organisms. The southern portions of Pangaea remained locked in a glacial ice age that had begun during the late Carboniferous. Massive ice sheets covered what would eventually become South America, Africa, India, and Australia, creating a world where tropical conditions could exist within a few hundred miles of glaciers. This extreme contrast between frozen and scorching regions created weather patterns that were both violent and unpredictable. Seasonal monsoons would sweep across the continent, bringing brief but intense rainfall to regions that might not see another drop of water for months. These flash floods would carve deep channels through the landscape, creating temporary rivers that would disappear as quickly as they had formed, leaving behind only dried mudflats and salt deposits. The lack of vegetation in many areas meant that there was nothing to hold soil in place, leading to massive erosion events that stripped away topsoil and created badlands that looked more like alien landscapes than anything we might recognize today. This was a world where survival required not just adaptation to extreme conditions, but the ability to cope with constant, unpredictable change. In this harsh new world, one creature stood out as the ultimate predator, a monster that combined sophisticated thermoregulation with devastating killing power. Dimetrodon, whose name literally means two measures of teeth, was a predator that would have been at home in our worst nightmares. This creature belonged to the synapsids, an ancient lineage that would eventually give rise to all mammals, including humans. This makes Dimetrodon one of our most distant and most terrifying relatives, a reminder of what our evolutionary lineage was capable of producing when survival demanded the ultimate in predatory efficiency. The most distinctive feature of Dimetrodon was the enormous sail that rose from its back, supported by elongated spines that projected upward from its vertebrae. This wasn't just an ornamental feature, it was a sophisticated piece of biological engineering that gave Dimetrodon a crucial advantage over every other predator in its environment. By angling its sail toward the morning sun, Dimetrodon could warm up its body temperature quickly, becoming active while its cold-blooded prey was still sluggish from the cool night. By turning away from the sun or seeking shade, it could cool down during the scorching midday heat. This ability to regulate its body temperature made Dimetrodon one of the most efficient predators that had ever existed. The genus included about 10 different species, ranging from relatively small forms about 2 feet long to absolute monsters that reached lengths of over 15 feet. The largest specimens could weigh more than 600 pounds, making them heavier than modern grizzly bears and far more dangerous. The skull of Dimetrodon was a masterpiece of predatory design, engineered to deliver bites that could crush bone and tear through the toughest armor. The front of its jaw was armed with massive canine teeth that could pierce through thick skin and muscle, while the sides of its mouth contained rows of smaller, serrated teeth that worked like organic saw blades. The jaw muscles of Dimetrodon were enormous, giving it the ability to generate bite forces that would have made it one of the most powerful predators of its time. When this creature clamped down on prey, there was virtually no escape. The combination of piercing canines and slicing side teeth meant that anything caught in those jaws would be both punctured and shredded simultaneously. But Dimetrodon wasn't just a brute force predator. It was also a sophisticated hunter that used strategy and stealth to capture its prey. Its powerful legs and muscular tail gave it the ability to move with surprising speed when necessary, allowing it to launch devastating ambush attacks or pursue fleeing prey across the harsh Permian landscape. The hunting strategy of Dimetrodon probably involved a combination of patience and explosive action. It would position itself near water sources or game trails using its superior thermoregulation to remain active during times when potential prey were most vulnerable. When the moment was right, it would strike with lightning speed, using its massive jaws to deliver a killing bite before its victim could react. While Dimetrodon dominated the terrestrial environment, the swamps and rivers of the Permian world were home to creatures that were equally formidable in their own domain. The largest of these was Archaeops, an amphibian that represented the absolute pinnacle of amphibian evolution. Archaeops could reach lengths of over 6 feet and possessed a skull that was both massive and incredibly robust. This wasn't just a large amphibian. It was a predatory machine that had evolved to take advantage of the abundant aquatic life that still existed in the remaining wetlands of the Permian world. The skull of Archaeops was particularly impressive, measuring up to 2 feet in length and built like a biological battering ram. The bone was thick enough to absorb tremendous impacts, suggesting that these creatures might have engaged in head-to-head combat with each other during territorial disputes or mating competitions. The mouth of Archaeops was filled with sharp, pointed teeth that were perfectly designed for grasping and holding struggling prey. Once this creature got its jaws around a victim, escape was virtually impossible. The teeth were arranged in multiple rows, ensuring that even if some were lost during violent struggles, there would always be plenty of replacements ready to take their place. The lifestyle of Archaeops was semi-aquatic, allowing it to exploit both terrestrial and aquatic food sources. In the water, it was a patient ambush predator that could remain motionless for hours, waiting for fish or other aquatic creatures to come within striking distance. On land, it could pursue smaller terrestrial animals, using its powerful legs to chase down prey across the harsh Permian landscape. The success of large predatory amphibians like Archaeops led to an evolutionary arms race that produced some of the most bizarre and specialized creatures in the fossil record. Different species developed different strategies for survival, leading to a diversity of body plans that seems almost surreal by modern standards. Some amphibians evolved incredibly thick, armored skulls that could withstand crushing bites from predators. Others developed elongated bodies that allowed them to move through dense vegetation or pursue prey in narrow waterways. Still others became filter feeders, developing specialized mouth structures that allowed them to strain small organisms from the water. The diversity of Permian amphibians was truly staggering, with species adapted for virtually every conceivable aquatic and semi-aquatic lifestyle. Some were tiny creatures no bigger than modern frogs, while others were massive predators that could take down prey as large as early reptiles. But this diversity came at a cost. The extreme specialization of many Permian amphibians made them vulnerable to environmental changes. As the climate continued to become more arid and the remaining wetlands began to shrink, many of these specialized species found themselves unable to adapt to the changing conditions. While amphibians were reaching their evolutionary peak, another group of creatures was just beginning an evolutionary journey that would eventually lead to the emergence of mammals. The therapsids, also known as mammal-like reptiles, were developing increasingly sophisticated adaptations that would allow them to thrive in the harsh Permian environment. These creatures were synapsids, members of the same lineage that included Dimetrodon, but they were evolving in directions that would prove to be far more successful in the long term. Unlike their sail-backed relatives, the therapsids were developing more sophisticated methods of temperature regulation that didn't require external structures. Some therapsids began to develop hair-like filaments that helped insulate their bodies, allowing them to maintain more stable body temperatures in the face of the extreme temperature swings that characterized the Permian climate. Others evolved more efficient respiratory systems that allowed them to extract more oxygen from the air, supporting higher activity levels and more complex behaviors. The skulls of therapsids also began to change in ways that would prove crucial for their descendants. The jaw muscles became more efficient, allowing for more precise control over biting and chewing. The teeth became more specialized, with different types serving different functions in processing food. Perhaps most importantly, therapsids began to develop more complex social behaviors and parental care strategies. Some species may have been capable of maintaining elevated body temperatures through metabolic heat production, making them functionally warm-blooded millions of years before true mammals appeared. While terrestrial ecosystems were undergoing dramatic changes, the oceans surrounding Pangaea were experiencing their own evolutionary revolution. The Permian seas were home to some of the most spectacular marine ecosystems that have ever existed, dominated by creatures that built massive reef systems and supported incredible biodiversity. The reefs of the Permian period were unlike anything that exists today. Instead of being built by corals, these massive structures were created by a variety of organisms, including bryozoans, brachiopods, and other invertebrates that work together to create complex, three-dimensional habitats. These reef systems were dominated by creatures called fusulinids, single-celled organisms that built elaborate spiral-shaped shells. Despite being unicellular, some fusulinids created shells that were several inches long and incredibly complex in their internal structure. These creatures lived in massive colonies that formed the foundation of Permian reef ecosystems. The reefs also supported diverse communities of brachiopods, crinoids, and other marine invertebrates that created underwater cities of stunning beauty and complexity. These ecosystems were some of the most biodiverse environments that have ever existed in Earth's oceans, supporting countless species of fish, arthropods, and other marine organisms. The Permian seas were also home to some truly spectacular predators that had evolved to take advantage of the abundant marine life. The sharks of this period had reached new levels of sophistication, developing hunting strategies and sensory systems that allowed them to dominate marine food webs. Some Permian sharks had evolved crushing teeth that were perfectly designed for breaking through the shells of brachiopods and other hard-shelled prey. Others had developed razor-sharp cutting teeth that could slice through flesh with surgical precision. The diversity of tooth shapes and jaw structures among Permian sharks was truly remarkable, reflecting the incredible variety of prey species that were available. The largest Permian sharks reached sizes that would make modern great whites look small by comparison. These ocean giants patrolled the ancient seas like living submarines, using their incredible size and power to dominate their marine environment. But sharks weren't the only predators in the Permian seas. The oceans were also home to a variety of other creatures that had evolved their own unique approaches to predation, including giant cephalopods, predatory fish, and arthropods that had adapted to marine life. As the Permian period progressed, the extreme environmental conditions that characterized this era began to take an increasingly severe toll on the planet's ecosystems. The formation of Pangaea had disrupted global climate patterns in ways that were making the environment increasingly unstable and unpredictable. The massive size of the supercontinent was creating temperature gradients that drove powerful atmospheric circulation patterns. These patterns brought violent storms, extended droughts, and unpredictable weather that made life increasingly difficult for many species. The interior of Pangaea was becoming increasingly arid as the distance from moderating ocean influences grew. Vast deserts were expanding to cover areas that had once supported diverse ecosystems, forcing many species to retreat to increasingly marginal habitats along the continental margins. The contrast between the glaciated southern regions and the scorching equatorial zones was creating atmospheric instability that manifested as violent storms and unpredictable weather patterns. These conditions put enormous stress on ecosystems that had evolved under more stable conditions. Deep beneath the surface of what would become Siberia, geological forces were building toward what would become the most catastrophic volcanic event in Earth's history. Massive amounts of magma were accumulating in underground chambers, building pressure that would eventually result in eruptions of unprecedented scale and duration. The early signs of this building catastrophe were probably subtle at first. Increased seismic activity, changes in groundwater chemistry, and small-scale volcanic eruptions might have provided warnings of what was to come. But these signs would have been invisible to the creatures living at the time. The geological processes that were building toward the great dying were operating on time scales that were far longer than the lifespans of individual organisms. The pressure was building slowly but relentlessly, setting the stage for eruptions that would fundamentally alter the planet's climate and ocean chemistry. Even before the massive volcanic eruptions began, the spectacular reef systems of the Permian seas were beginning to show signs of stress. Changes in ocean chemistry, temperature fluctuations, and other environmental factors were starting to affect the delicate balance that had allowed these ecosystems to flourish. The fusulinids that formed the foundation of many Permian reefs were particularly sensitive to changes in water temperature and chemistry. As conditions began to change, these organisms found themselves unable to maintain their elaborate shell structures, leading to the gradual collapse of entire reef systems. The loss of these reef habitats had cascading effects throughout marine ecosystems. The countless species that had depended on reefs for food, shelter, and breeding grounds found themselves without suitable habitats, leading to population declines that would make marine ecosystems increasingly vulnerable to further environmental changes. On land, the increasingly harsh conditions were also taking their toll on terrestrial ecosystems. The plant communities that had managed to survive the transition from the Carboniferous were finding themselves unable to cope with the increasingly arid and unpredictable climate conditions. The loss of vegetation had cascading effects throughout terrestrial food webs. Herbivorous animals found themselves with less food available, leading to population declines that affected the predators that depended on them. The complex food webs that had supported Permian biodiversity were beginning to unravel. The soil systems that had developed over millions of years were being destabilized by the loss of plant cover. Without vegetation to hold soil in place, erosion was accelerating, leading to the formation of badlands and other degraded landscapes that could support little life. As the Permian period drew to a close, all of these environmental stresses were building toward a perfect storm of destruction. The geological forces building beneath Siberia were reaching a critical point, while ecosystems on both land and sea were already showing signs of severe stress. The stage was set for the most catastrophic mass extinction in Earth's history, an event that would come to be known as the Great Dying. This extinction would eliminate over 90% of marine species and 75% of terrestrial species, bringing the entire Paleozoic era to a violent and dramatic end. The creatures that had dominated the Permian world, from the sail-backed predators to the giant amphibians to the spectacular marine reef builders, would all disappear in what was essentially the blink of an eye in geological terms. The incredible diversity that had taken millions of years to evolve would be wiped out in a catastrophe that lasted only a few thousand years. The journey we've taken through the Permian period has revealed a world that was both magnificent and terrifying. A planet where evolution was conducting its most extreme experiments under the harshest conditions imaginable. We've witnessed the rise of sail-backed predators like Dimetrodon, explored the world of giant amphibians that ruled the remaining wetlands, and seen the early evolution of the mammal-like reptiles that would eventually give rise to our own lineage. But we've also seen how this incredible diversity was building toward the most catastrophic ending imaginable. The environmental stresses that characterized the Permian world were pushing ecosystems to their breaking point, setting the stage for the Great Dying that would nearly end complex life on our planet entirely. The story of the Permian period is ultimately a story about the limits of adaptation and the fragility of even the most successful ecosystems. Despite producing some of the most innovative and successful creatures in Earth's history, the Permian world was ultimately unable to survive the environmental catastrophe that brought it to an end. In our final episode, we'll witness the Great Dying itself and explore how the few survivors of this catastrophe managed to rebuild the biological world from almost nothing. We'll see how the end of the Permian set the stage for the rise of the dinosaurs and the beginning of the Mesozoic era. If you've been amazed by this incredible journey through Earth's most extreme prehistory, make sure to smash that like button and subscribe with notifications turned on. The story of life on our planet is filled with triumph, tragedy, and survival against impossible odds, and we're approaching the most dramatic climax of this incredible tale. Drop a comment below and let me know which aspect of the Permian world surprised you the most. Were you more fascinated by the thermoregulation strategies of Dimetrodon? Or were you more impressed by the sophisticated reef ecosystems that dominated the Permian seas? And remember, the most catastrophic chapter of this story is still to come, as we witness the end of an entire era and the beginning of a new chapter in the history of life on Earth